So let X be a Banach space, Y be a norm space, and Tn be a sequence of bounded linear operators from X to Y, with the property that limit n tending to infinity Tn of X exists for all X belong to capital X. And now the formula T of X is equals to limit n tending to infinity Tn of X defines a bounded linear transformation. So what I have is a family of operators, or like not a sequence of operators rather than family, sequence of operators, and then they're all bounded linear operators. And I'm saying that the limit of sequence of bounded linear operators also defines a bounded linear operator. That's basically the idea behind. So I can put it in simple way. I can say that the limit of a sequence of bounded linear operators is also a bounded linear operator. So now the first thing that I want to prove is that the T operator, this function T, this is consideration, it is linear. So the linearity, I prove that I just write this T as it is, just use rather than x alpha x1 plus alpha x2, and I know that Tn are all bounded and linear operators. So if I know that bounded, I can move the limit inside. Well, I know that Tn is also linear. So first I can take these Tn's inside, and then I take those limits inside, and hence I can write it like this. So this is easy. So I just showed that this function T is linear. Only remains to be shown that this is bounded. What would I need to show that T is bounded? If I can show that the norm of Tx, so if you just look at this step for a sec, that this is less than some m times norm of x, then I can say that this T is bounded. That's the goal. And the fact that T and x converges for each x belong to capital X, it's given, implies that the supremum over n Tn of x should be less than infinity for all x belong to capital X. Now, of course, this is what it means for T and x to converge. It exactly means this. And we know that according to the uniform boundedness principle, if x is, let me say, let x be a Banach space, y be a norm space, then point-wise boundedness implied uniform boundedness. So I know that if it is point-wise bounded, then uniformly bounded too. So till this step, everything is clear. I say that, okay, the supremum over all n belonging to natural numbers of Tn is less than infinity, and I define that supremum to be m. And hence I can say that the norm of Tnx is less than equal to norm of Tn, norm of x, and this, if I take the supremum over it, then I can see that it is less than or equal to m times norm of x for all x belong to capital X. The next thing that I do is I just write T of x as limit n tending to infinity norm of T of x. So let me write that T of x is equals to the limit n tending to infinity Tn x, and if I just apply a norm on both sides, then I can say that norm of T of x, and since norm is continuous, so I can take the limit outside, I can say that it is equal to the, well, let me just write it this way. So Tnx, okay, but I know that even as my n tending to infinity, even this limit is less than equal to m times norm of x. Well, this is just an estimate of it. Even if the n tends to, well, if I, okay, let's look at this way. I have a norm of something and the limit n tending to infinity. So it has, of course, has to be less than m times norm of x, because this is what I already know. So I can, since my norm as an operator is continuous, what I can do is I can write this as limit n tending to infinity norm of T and x, and this norm of t and x is less than equal to m times norm of x. So limit stays the same, but since m comes here, then it does not have any effect. So it is just less than m times norm of x. Thus I can say that indeed t is also bounded, because norm of t of x is less than equals to m times norm of x for all x belong to capital X. So let x and y be norm spaces and t x to y be a linear mapping. And what I'm saying is that if mt has an interior point, then t must be surjective. Okay. In particular, every open mapping t from x to x is surjective. So let's see it this way. If mt has an interior point, so let me take y star, which is an interior point. This is, so if y star is an interior point of mt, then there exists a r greater than 0 such that I can draw a ball of radius r around y star, and that ball is a subset of mt, because this is what I mean when I say that mt has an interior point y star. Now since mt is a subspace of y, it follows that the ball of radius s around 0, so I can, if I just, a ball of radius s around 0 can be written like this. So if I minus y star, so my star, it becomes a ball of radius 0, and then I divided by s and multiplied by, divided by r and multiplied by s. So this is and now I see that this is a subset of mt, because first of all, if I say that image t was a subspace, then by default it means that I can find a ball of radius s around 0, because every subspace has to have the 0 element in it. And even if it's, and the other argument is that, okay, if mt is a subspace, then I can do the translation argument and the scaling argument, and yet the resultant is still in mt. So all we have done till now is we have taken an interior point and we have shown that a ball of radius r around that point is completely within mt, and here we are showing that the ball of radius s around 0 is also as a subset of mt for each s greater than 0. And hence we know that y is the union of all such balls with s greater than 0. Of course, well, of course, and this is a subset of mt, because this is what I showed. So if a ball of radius s around 0 is a subset of mt, and since mt itself is a subspace, then I can use the scaling argument to increase this s, and I can thus say that all such balls would be a subset of mt, and mt itself is a subset of y. So I can say that mt is equals to y now, and thus I can say that this t is surjective. Okay, very nice. And the next thing that I would like to talk about is, if 0 is an interior point of tb10, then t is open. So let's see it this way. So if u is an open subset of x, then for each x belonging to u, there exists a r greater than 0 such that I can draw a ball of radius r around that x, and that ball lies completely within u, the subset of u. So this is what it means to be an open subset of u. Okay, and therefore if I just apply t on both sides, so t of x plus r tb10 is a subset of t of u. Just apply t on both sides. Now since 0 is an interior point of tb10, there exists a s greater than 0 such that a ball of radius s around 0 is a subset of tb10. Of course, this definition of course makes sense, we just saw this there. And hence now if you just split it into pieces, we see that this is exactly I can write it as this. So yeah, I can just separate the tx out and rbs, but I know that this bs is a subset of tb10. So let me reformulate it. So this would be, this thing here would be a subset of, say, tx plus r, and bs 0 is a subset of tb10, so I can write it as r times tb10. But I know from before that tx plus r tb10 is a subset of T of U, and hence I can say that I can draw a ball of radius Rs around T of X, and it is a subset of Tu. And thus, if 0 was an interior point of TB10, I showed that T is open because this openness was shown because I took an open set in X and it got mapped to an open set in Y. The open set in X was this, and this got mapped to an open set in Y. This was my open set and it got mapped. So T of X plus R TB10 is an open subset of T of U. I just proved this, and hence I showed that if 0 is an interior point of TB10, then T is open. So now we finally come to the crux of this video, and that is the open mapping theorem. So let X and Y be Banach spaces and T from X to Y be bounded, linear and surjective mapping. It follows that T is open. So by T is open, I mean that T maps open sets to open sets. So the proof flows as follows. So suppose T is surjective, it implies that Y is equals to T of X. Well, why? Because surjectivity always means that Y is equals to image of T or just T of X. Now X can be written as the union of infinite number of balls from n equals to 1 to infinity. T is continuous, so it can come out inside, and then I can replace it with the closure of this. Well, and now when I have this sequence of non-empty bounded sets, I can say that according to Bayes' theorem, if I have a sequence of closed subsets of X with the property that the interior of the union is non-empty, then exists a K belonging to N such that interior of AK is non-empty, and thus I can say that. So I can say that using Bayes' theorem, there exists a N star belonging to N such that the closure of TB N star 0 has an interior point. Now if this set has an interior point, then the closure of TB10 has an interior point. Why so? So my proposition is, if the closure of TBN star 0 has an interior point, then the closure of TB10 has an interior point. Now the proof flows as follows. So note that the closure of TBN star 0 is equals to N star times the closure of TB10. Now let X be an interior point of closure of TBN star 0. So there exists an open set. Now this open set does not necessarily have to be a ball, it could be any open set. So this is the twist in this case. So earlier my definition of interior point was, okay, if I have an interior point, then there exists a ball and this ball completely lies within the set. But now I am saying that it could be any open set, it does not have to be a ball. So if TBN star has an interior point, then there exists an open set W, that this set W is completely contained in TBN star 0 and X is an element of W. So now I just take N star out from here and divide everywhere by N star. So 1 by N star W is an open set such that 1 by N star X belongs to 1 by N star W, which is a subset of closure of TB10. So I just proved that if closure of TBN star 0 has an interior point, then the closure of TB10 has an interior point. But it is not the same interior point, of course. There are two different interior points. Now this is still here. You see the way these proofs are structured. So in order to decode every line, you have to go through a different proof. So every line has a story. Anyway, let's go back to the topic. So it follows that the closure of TB10 has an interior point. Now there exists an A belonging to the closure of TB10 and R greater than 0 such that this ball is completely in the closure of TB10. Now remember that from TBN star 0 to TB10 I used any open set, and now when I am in TB10, the closure of TB10, I again use my ball notation. So I can say, okay, if this is an interior point, then there exists A such that the ball of radius in my space Y around A is completely lying in the set which is closure of TB10. Now the closure of TB10 is symmetric, that is, this is equals to this. Why so? Well, I know that if I have a ball of radius 1 around 0, it is equals to the minus of ball, because yeah, ball is what, a set of points. But the property of a ball, if you analyze correctly, is that all those points inside the ball, they are like copies of each other. So if I take negative of all the points in my ball, it would still remain the ball. So negative of this region, would be this, negative of this would be this, and so on. So yeah, I take both the balls, I apply T on both sides, and then I close them. So okay, TB10, the closure of TB10 is symmetric. So if A belongs to closure of TB10, then minus B, A also belongs here. Now hence, I say that my ball of radius R centered around 0, it can be written like this, of course, and this is a subset of these two things. So well, A was a subset of this and this was a subset of this. So this ball of radius R around 0 can be written like this, and this is a subset of these two things. Why? Because A was a subset of this and BRYA is a subset of this. So the ball of radius R are centered around 0 is a subset of the closure of TB to 0. And now I see that looking at this argument, I can say that the ball of radius R by 2 is a subset of TB10. Well, in order to justify this, if you just look at this argument like this, so this is a subset of the closure of T, and now going from this step, I can just take this 2 out here, make it 1, make it 2, and make it 2, and get the 2 cancelled, and it still remains a subset. So from here to here, no problem. So now I just showed that I can draw a ball of radius R by 2 around 0, and it is an open set in the closure of TB10. Now we show that the ball of radius R by 8 is an open set in TB10 rather than the closure of TB10. So here I already see that 0 is an interior point of the closure of TB10 because this ball lies, the ball is a subset of this. But I want to show that 0 is an interior point of closure of TB10 because if you look at this lemma, that if 0 is an interior point of TB10, then T is open. Now I know that if 0 is an interior point of TB10, then T is open. Now how would I show that 0 is an interior point of TB10? So starting from this point onwards, so if I show that I could draw a ball of radius R by 8 around 0 and this ball is a subset of TB10, then I can show that 0 is an interior point of TB10 and then hence T is open. So from this point onwards to this point onwards, it's just a technical argument. So it's a technical algorithm. I construct inductively a sequence such that the sequence, that the norm of xn is contained by this term and the norm of y minus t of x1 till xn is contained by this term. And now again I choose my x1 such that the norm of x1 is less than 1 by 4, so I just have to put the value of n equals to 1, and similarly here also, and it should be n2. So yeah, it exactly makes sense. Now this is possible since y is belonging to the ball of radius r by 8 centered around 0 and it is a subset of this one, as we have seen before, because let y, so my initial assumption was y is a point here. Okay, so till here no problem. And for n equals to 1, 2, 3, I choose xn plus 1 with the property that xn plus 1 is this and similarly this is this. So I just increase the value of n to n plus 1, and I get this equation. Now this is possible since y minus t of this lies in a ball of radius r by 2 to the power n plus 3, which is completely contained in this. And thus I showed, so now it's not necessary that you need to go through this argument. All you need to know from this point onward is that I chose a y and in this set and proved that y belongs to this set. So this means that the ball of radius r by 8 centered around 0 is completely contained within T B1 closure 1 by 2 0, which if you see above is completely contained in TB10, and thus I show that TB10 has an, so I show that 0 is an interior point of TB10, and I can say that hence T is open. So now the summary is any bounded surjective linear mapping is open. How I went to the proof? Well, again, I made use of the fact of surjectivity. With surjectivity, I showed that y is equals to the union of the closure of TBN0, where n goes from 1 to infinity. And then I showed that since this closure of TBN0 is a sequence of non-empty sets, I can make use of Bayes' theorem to find an interior point here. And once I find an interior point, I construct a ball. And again, I showed that the ball of radius r by 2 centered around 0 is completely contained in the closure of TB10. And using this argument and a very technical algorithm thereafter, I showed that the ball of radius r by 8 is completely contained in TB10. And making use of the proposition that we did above, we can say that T is open. Now this is a very beautiful but at the same time tricky theorem, so let's look at it very calmly. So let x and y be Banach spaces and T from x to y be a bounded linear bijection. Now as soon as I heard this word bounded linear bijection, I should instantly think that okay, T is open because x and y are also Banach spaces. And it follows that T inverse from y to x is also bounded, so that T is a topological isomorphism, which means that it has a continuous inverse. Now the open mapping theorem shows that T is an open mapping. Now I'll explain this argument in my words. So what does T continuous means? So T being continuous means that, so this is space x and this here is space y. So I say that if TU is open, then U is open, like this was the definition of F being continuous. If F inverse of phi is open, so like I always used to write that okay, F is a function which takes me from x to say y, and I always used to say that okay, that if say y is open, small y is open, then F inverse of y would also be an open here. So this is what T continuous means. Now what does T inverse continuous mean? So it shows that if U is open, then T of U is open. This means that T inverse is continuous, but we know that T is an open mapping, so therefore if U is open, then necessarily T of U is open. So therefore I have that T inverse is continuous, and thus I can say that T is a topological isomorphism because it is surjective and it has a continuous inverse. Norms, so I say that two norms, so I describe the two different norms as 2 lines and 3 lines. They are equivalent if they generate the same open sets, so that the collection of sets measured by this norm is equals to the collection of sets measured by this. So basically this is a collection of points, and measured by this norm they should be exactly equal to the collection of points measured by this norm. So that's the concept of equivalent norms. Now what I want to say is that the lemma, so I need to use a lemma. So lemma says that two norms are equivalent. So two norms are equivalent if and only if
there exists C1 and C2 such that norm of x is less than C1 norm of x in 3, like in the different norm, and this in 3 norm is less than equal to C2 in 2 norm. So these two norms are equivalent if and only if there exists C1 and C2 such that these two conditions are satisfied for all of x.
two Banach spaces. And now suppose there is a constant c greater than 0 such that as soon as I see this, I am reminded of a fact. I am reminded of a fact that tx is less than or equal to m of x. So if this was the condition, so I write this t of x as x1. So I have an operator which goes from this space to this space. Let me call it as the identity operator. So identity takes an element. So let me write it this way, x2, and the identity takes it to x equipped with one norm. So if that's the case, so I of x2, so I of x in space 2, so let me write it this. So I of x in my space 2 is, or in space 1, because I is taking an element from 2 to 1. So I of x in space 1 is less than equal to c times of just x in space 2, because I is going from 2 to 1. So yeah, that's better. So I goes from this space to this space. So I of x in this space is less than equal to c times norm of x2, which is exactly which is given here. So if I just rewrite it, so I of x, anything of I is just that thing. So I think I can write x1 less than or equal to c times norm of x in the 2 norm. And thus I can now make use of the inverse function theorem. So what did I have? So I have that I be an identity transformation, so which is trivially linear and bijective. And by hypothesis, by this hypothesis, so it should be from 2 to 1, because that's why I always had norm of tx is less than equals to. So this space is where, from which space I am going to, and this is the space where I am. Yeah, so t takes me from this to this. So I can say that, okay, I have identity which is linear, bijective and bounded, because this thing is given. So if I have linear, bijective and bounded, bam, I maps open sets to open sets. And again, if this is the condition, then I can say that the inverse is also bounded. So if I have I inverse which goes from x, say 1 space, to x 2 space, then I can say that this is bounded because of inverse function theorem. And if this is bounded, then I can just write I inverse of some element here. So it would take me here. So this time I am in space 2. So I can just write x space 2 less than equal to some c tilde in my original space. So I can say that because I just proved that the inverse is bounded. So this condition holds. And if this condition holds, so if I show that these two norms are equivalent if and only if this also holds true and this also holds true, which does holds true in our case. So I can say that this norm and this norm are equivalent for x.